All right, so we're going to go through some notes here for section 1 of chapter 4. All of this stuff, there's a lot of things in this section, lead to our atomic model according to Bohr. So we got to talk about electromagnetic radiation. We got to talk about the dual wave particle nature of light. And we got to talk about photoelectric effect and hydrogen emission spectra. So a lot of stuff to cover. Try and get through it quickly, but we're starting out with electromagnetic radiation. So it's a form of energy that travels in waves. There's a spectrum of all of the types of electromagnetic radiation that I can show you in a picture. You may recognize this from Mr. Hagg's class, possibly, a poster of this. You can see that as you go from the left-hand side to the right-hand side of this picture, the waves tend to get smaller and smaller and smaller. So I have radio waves over here on the left, and I have gamma rays all the way over here on the right. And we're supposed to be able to recognize that as I go from left to right, certain things will be true, right? You have these different things that are being related. The length of the wave is longer on the left than on the right. So as I go from left to right, my wavelength decreases, and I use this lambda symbol for wavelength. As I go from left to right, the frequency of my waves is actually going to increase, and frequency is related to energy, which is also going to increase as I go from left to right. So I need to know all this stuff. I also need to know that I got my visible light spectra in here that is going to be somewhere in the middle, right? But from that standpoint, when I have a picture in my notes, again, you got longer waves that end up getting shorter and shorter and shorter, and this is really hard to draw, so it's okay if yours looks bad like mine. But otherwise, somewhere in the middle here, we have the things that we're concerned with. We have those colors of the rainbow, Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, violet. Now, just below red is infrared. Just above violet, in terms of energy, is ultraviolet. So we're going to talk about those things later in these notes. But again, there were other points of interest, right? You got things like radio waves and gamma rays and X-rays and stuff that could go on this spectra. So radio is over here on the long end. You got gamma rays way over here, X-rays in here, and then maybe even throw in a microwave, because you guys know what that is. But otherwise, just understand that different parts of electromagnetic radiation are related to each other. We got to relate wavelength and frequency. And it turns out that wavelength times frequency gives you the speed of light, which is 3 times 10 to the 8th meters per second. So an example of some kind of calculation you may do with this, right? If I knew the wavelength of light that I'm dealing with, so if I went backwards and I open this up again and I look at red light that's at like 700 nanometers, right? And purple's over here is at like 400 nanometers. If I knew a specific wavelength, so let's say it's that red that's 700 nanometers, excuse me, pen doesn't want to write right here. Not sure what the deal is. But anyway, 700 nanometers, right? In order to figure out the frequency of this light that's at 700 nanometers, its wavelength is 700 nanometers, I have to take the speed of light, which is 3 times 10 to the 8th meters. And again, this is actually a compound unit, so I should put the seconds on the bottom. I'm going to divide by this length, that nanometer, because meters could ultimately cancel. They're not going to cancel unless I actually know the difference between nanometer and meter. So I should know that there are 10 to the 9th, a really big number of nanometers in a meter. So in order to do this calculation, I have to have that conversion factor in there too. But ultimately, when I multiply, divide, and get an answer, right, the important thing that I recognize here is what the unit's going to be. I don't care what the number is right now, but the unit is 1/2, right? Wavelength units are simple. They're some form of a meter, right, a length, because they are literally lengths. You have a wave that has two like points here and here, and you're just measuring the distance between those 2 points, right? If I had a continuous picture of a wave, excuse me, I need to draw that a little bit better, right? Really, you could just take any 2 points that are similar, like the peaks or the troughs, and you can measure those. But technically, I'm supposed to measure from as I'm going along like kind of a middle of this, right, from where it went down to when it comes up, and then when it goes back down. That's how I measure wavelength. But any of those things would technically work. But again, it's just going to be a length, a literal length in meters. And it might be a micrometer or nanometer because it's a really small wavelength, like the color red. But otherwise, frequency, its unit is this 1/2, right, which sometimes is written as an inverse second, right? Or sometimes this unit's used, hertz. And you may be familiar with that, especially if you're inclined musically. So pitches, right, have to do with frequency. So when you're singing and you're trying to sing different notes, you're trying to create a specific pitch, right? But this could go all over the place. We could spend a whole quarter talking about electromagnetic radiation and how you can apply all this information. But for right now, we just need to know that light travels in waves, right? That light that we see, that visible light, there's a wavelength and frequency associated with those waves. And then we got this photoelectric effect. Again, it says light electric effect essentially there, right? You can have this emission of electrons from a metal when light shines on that metal. It depends on the frequency. There are only some frequencies that cause electrons to jump, right? And essentially, it'll be these frequencies on my spectrum from before that are considered ionizing radiations, right? So I'm going to need high energy frequencies to get an ionizing radiation to occur, to get electrons to jump out of an atom. So it works best with the specific frequency, and actually the best frequencies are found in UV light, right? Otherwise, quantum, the minimum amount of energy that can be lost or gained by an atom, right? So I'm talking about this photoelectric effect. An electron can absorb a certain amount of energy and then jump out of an atom. Well, that energy is called a quantum, right? And energy can be related to frequency, as is shown. Again, if I was going to deal with a unit situation here, if I had some frequency and I wanted to figure out how much energy it's associated with, I would take that frequency, which again would have a weird unit. It'd be 1/2, right? And I'd take it times this h, this Planck's constant. That would be 6.6, excuse me, lost contact there, 6.626 times 10 to the negative 34th, which is a really tiny number, notice, joules. But this unit is weird too. It's a compound unit, but both things are on the same level. So I could put a joule here and times seconds. Both of those things go on top instead of one on top, one on bottom. And that's how the second goes away. And you end up with a label that's joules for your energy. So if we did calculations with that, it wouldn't be that difficult. You could do it, but not going to be a main portion of the chapter that we're doing. So a photon is a particle of electromagnetic radiation having zero mass and carrying a quantum of energy. So again, when light strikes that metal, a photon could be absorbed by electrons in that metal. and those electrons will jump, right? So again, very, very confusing because we talked about the light traveling as a wave being part of this electromagnetic spectrum, but we're also talking about particles, and those are different things, right? So I have this wave of energy, but there's particles that carry that energy. So that's that dual nature of light that was in the objectives. And this was enough to confuse early physicists and chemists, from the mid 1900s. This was a very confusing concept, going from one thing to the next. But anyway, a photon is a particle of electromagnetic radiation. They didn't think they had particles, but now they do, right? That has zero mass and carries a quantum of energy. So then we start talking about ground state, excited state. And ground state is the lowest energy state of an atom. Excited state is some state with a higher energy than ground state. So hopefully if you got some blanks filled in, this picture on the next slide is really what we're talking about at the end of the day. I have this atom, this hydrogen atom, that has one proton in the middle, and then it has these shells, right? An electron typically would occupy whatever shell it can be in that's closest to the center. This electron right now is in ground state. And in order to get it to change from ground state to another state, it's going to have to absorb a certain amount of energy. Because in order to jump up to a higher energy level, to this first energy level, as opposed to the 0th one, so we always start at 0, go up 1, 2, 3, 4, right? If it's going to jump from 0 to 1, it's going to have to absorb energy to do that. And it's probably going to absorb a photon, right? A quantum of energy that's in light. So if electrons in an atom absorb light energy, they can jump, right? There's only so many places they can jump to, though, right? They can go from 0 to 1, 0 to 2. They can't land in between, right? In the classroom, I usually talk about jumping from one desk to the next, right? It takes a certain amount of energy to jump one desk away from you, but it takes even more energy to jump 2 desks. And you're not supposed to land in between because then you crash and burn, right? So the same thing's true for these atoms. There's only so many energies that could be absorbed by those electrons because it can either go from 0 to 1 or from 0 to 2 or from 0 to 3, but there's nothing in between those energies. Otherwise, the reverse is also true. If I have an electron that's at a high energy state, an excited state, it can drop back down to a lower energy state, whether it's 1 lower or 2 lower or whatever. But if an electron's going to drop down towards ground state, it has to emit energy. It has to lose energy. And so the opposite of what happened before, instead of absorbing a photon of light, that electron would typically emit some photon of light. All right. So that brings us to our next idea. This all seems jumbled, but I promise it does come together eventually. So ground state, excited state. Electrons can jump up to excited states if they absorb a certain amount of energy, a photon of energy that carries a quantum of energy. Whereas electrons that are in excited states can drop down and release energy as a photon, right, containing a quantum of energy. So this is actually the same picture, right? But we're going to take it to the next step, right? Photons absorbed and emitted have specific wavelengths related to the energy gained or lost by an atom when an electron moves from one orbit to another. So think of this as that hydrogen atom from before. I have that ground state down here, right? And then I have 1, 2, 3, 4, 5 different excited states that an electron can be in. But if an electron is in that highest energy state, in this 5, and it drops all the way down to 0, that amount of energy that would be released would be greater than the amount of energy needed to drop from 4 to 0, which is greater than the amount of energy needed to be released to drop from 3 to 0, which is greater than 2 to 0, which is greater than 1 to 0, right? Pretty easy to understand, especially if, again, we were thinking about jumping from one desk to another. A bigger drop, a bigger distance to jump is associated with more energy. But then I don't always have to drop to 0. I could also drop from 5 to 1, and from 4 to 1, and from 3 to 1, and from 2 to 1, right? So these energies can also be seen and talked about. So again, we talked before about how it's almost impossible to model an atom just because of the sheer size and magnitude of the differences between one shell and another. Technically, this arrow here, right, the one that goes from 5 to 1, should actually be smaller than the arrow going from 1 to 0. It's not, because I can't make a perfect model for this because it wouldn't fit on the screen. But you just have to understand, as I go from left to right, all of the energies are decreasing constantly, right? So even though this 2 to 1 looks bigger possibly, even though this drop from, I'm going from 5 to 2 now, is bigger than this 2 to 1, it's not actually supposed to be. It's just a limitation of what I can do. So this is smaller than this, and then this one's smaller than, obviously, and then my 3 to 2 is smaller, right? I have all these different options. I can even go from 5 to 3 and 4 to 3, and I can go from 5 to 4, and those would be smaller still. Now, the reason why I drew all these things out is because I go to this next slide, and don't worry about the stuff at the top quite yet. Just look at this picture at the bottom. In class, we will look at emission spectrum, right? Which would be the bottom actually down here where there's just one wavelength of light at a time. So there's red over here, there's this teal color, there's a bluish color, and there's a purple color. This actually is for hydrogen, right? So the element hydrogen will emit these different wavelengths of light. Ignore this continuous spectrum up at the top, or technically it's an absorption spectrum. But what we want to understand is that this model that we're drawing here is related to these spectra that we can see in the classroom. What I'm supposed to understand is that some of these energies are bigger than others, right? Like these energies are the biggest, this group. And those quanta, those energies that are turned into a photon carrying a quantum of energy, that light that's going to be emitted by the atom has too much energy and has too short of wavelengths for us to actually see. If I go all the way back to my electromagnetic spectrum, light that's too energetic and too short of wavelengths for us to see is UV, right? It's ultraviolet. So these drops would be associated with UV light that we wouldn't actually be able to see. These three energies actually have too little energy for us to be able to see them, right? They're too small of energies. They have too small of frequencies. Their wavelengths are too long, actually. So they're actually on the other end of that spectrum. Those are actually infrared, right? So we're trying to explain what we see when we look at a hydrogen atom. We can't see infrared light. We can't see UV light. So we're not going to see any of those energies being released by a hydrogen atom. But we are going to see these energies, right? And what you're supposed to understand, again, red has less energy than purple, right? So if I look at that emission spectrum one more time, there's a purple color that's emitted by hydrogen, but there's also a red color that's emitted. The red color has to be lower in energy, which means it has to come from a smaller drop. So the smallest of these 4 drops is from 2 to 1. So when this electron sitting here drops down to that first energy level, it's going to have to emit energy that happens to have a frequency and wavelength that we can see, and it's red. Whereas on the other end, this drop would be much bigger and have more energy. This is going to be a purple color, right? It would have a shorter wavelength and a higher frequency and more energy. So I drew those wavelengths smaller than these red wavelengths for a reason, right? They're supposed to be kind of an indigo blue color one as well. So that would be right here. These waves need to be a little bit longer than the purple waves, but not quite as long as the red ones over here. And then finally, there's a teal color. As this electron drops down to 1, it'd just be somewhere in between the blue and red. So even if I don't draw these perfectly to scale or anything, right, this would be a slightly longer wavelength than the regular blue ones, but not as long as the red ones. So we can actually model and understand exactly where that light that we see is coming from. We can see these different wavelengths, frequencies, coming from a hydrogen atom that's electrified. So when we look at this in class, we know what it is we're looking at. Again, there are other things that we can't see. There's this UV light that's being produced. There's actually infrared light that's being produced as well. The infrared light is something that we can actually feel because the glass tubing gets hot. And the glass is absorbing that infrared light that's being emitted. We can't see it, but we can feel it when it's all said and done. The UV light, on the other hand, we'd have to have some other way to detect it. So when we look at this stuff in class, and we'll talk about the difference between these spectrums, these different types of spectra in class, but ultimately I need you to be able to understand where those colors came from that we saw. And just for hydrogen, because hydrogen is the simplest example of this, and it's the only one we can actually accurately draw this way and predict what colors we might see. So hopefully some of this made sense. I know it's all kind of seems random and it's jumping around, and hopefully I give you a better explanation in class 2 for things that you don't quite understand. But at this point, I think we're good for this video.